I want to start this lecture with a news flashback. So this was an article in New York Times front page little over a year ago, May 5, 2011. So semiconductor news nowadays mostly doesn't make to front page of New York Times unless it's Solyndra going bankrupt or something. So I was pretty excited when I saw this on the front page of New York Times, and it was a press announcement. This article was a follow-up of a press announcement from Intel, and it had I read through it, and it there's three main points that this article says. It says Intel is going to use 3D transistors for 22 nanometer. And usually whenever they make announcements like this, they will gather all the star power, Gordon Moore will come out from the woodworks and make a statement like this is the most radical shift in transistor technology in 30 years. And the other part which is mentioned was there's a competing technology, and that's SOI technology, and we'll talk about that as well. Same coverage in Wall Street Journal. I usually switch between New York Times and Wall Street Journal. Usually I find Wall Street Journal has better technology coverage because primarily they have an office here, they own all things deep. But anyway, so this article again, similar theme. It says that they want to use this FinFET as a weapon to get into the tablet market. Right, so so it's a very popular topic, and so one way to look at popularity is, as I said, we use all the analytics available to monitor, the videos that we upload, who's watching what, where is he watching it from, when is he watching it, right? So, I uploaded these, and somehow I found the most popular videos that people watch are, FinFET related videos on the site, and we track, where they are watching it from. It's kind of blurred out, but and I'll talk more about this analytical part, analytics later in this course. We are still building up this user data, and we'll talk more of that later. So what prompted them to make this big announcement? And so then I went back and looked at, they put out a press release, and at part of that press release I had also made a video. I've uploaded that on the site so you can take a look. But what prompted them to make this claim was, what they were saying was this technology, which is the FinFET technology, that is, this transistor is now 3D in the shape of a fin. They were saying this is 37% faster than a 32 nanometer planar technology, or it allows them to operate at a voltage reduction of 0.2 volt. That is, usually operate around 1 volt, but using this technology they want to operate at 0.8 or 0.7 volts. And so they made some pretty bold statements. You should take this with a pinch of salt, though, that they're comparing it not to they're comparing 32 nanometer planar to a 22 nanometer 3D. A fair comparison would have been to a 22 nanometer planar. So when I was preparing this lecture, I was watching their press video, and somebody did ask them that you might have made 22 nanometer planar in your lab too. How does it compare to that? So they didn't give a very clear answer on that. But the reason they were able to accomplish this was because so the reason they stated was that they can operate at a lower voltage because they can lower their VT. And the reason they can lower their VT is, so this is your planar device, and this is a tri-gate device. So what the main difference is that this has a much steeper subthreshold slope, or another way to say is it has a lower subthreshold slope. So if you look at this curve and this curve, this is more steeper. So it reduces your off current, and that for the same off current you can shift this curve parallel. And when you do that, essentially what you're doing is you're reducing your threshold voltage, and that allows you to operate at a lower voltage. So this was, the press announcement. So to give you some specs, they want to. These are the power envelopes typically associated with different microprocessors that go into your home computer. You can use more than 50 watts. It's often said if you want to save power or save an electricity bill, you should switch to laptops because they have a lower power envelope, and handhelds maximum we discussed around 4 watt for ASICs, but a typical power load for most application is less than a watt. So they want to go from here to here using this FinFET device, and let's see whether it's possible, whether the claims are true. So we'll look into that later in this lecture. But they also released this picture along with their press release, and what they compared here is 32 nanometer planar technology with a 22 nanometer fin technology, and you can see the fins over here. So these fins are these lines over here. These are the fins, and you can see multiples of them. And then there's a gate which is wrapping around this fin. So this is gate 1, this is gate 2, this is gate 3, and so these are the source drain, and this is the gate. And over here also you have this source drain and gate, but they are in one single plane. But in comparison, you have this. You can clearly see in this image that they have these fins. So, but they didn't. So it's always said, a picture is worth 1,000 words. So there's a lot more information that you can actually figure out by looking at this picture, which they did not provide. One thing which I uploaded in the video, you can figure out. They used spacer aligned double patterning, and you can. Sam, who came last week, talked about it as well. So the way you can figure out is you can clearly see that these two fins have one spacing between them. These two fins are closer, and these two fins are far apart. Then these two fins are closer, and these two fins are far apart. And that can only happen if you're using a spacer-based lithography. Another question which comes to mind looking at this picture is, this is one gate. So this is one transistor source drain. This is one gate, so this is another transistor. Why do they have a gate over here? Why do they have a gate line here and here? This transistor is essentially hanging. I mean, it's not doing, this gate line is not doing anything, right? So this was released in May 2011. But the actual chips didn't come out until a year later. So this technology was kind of delayed by a year. They usually say that they release it every 2 years, but this was delayed by a year in production. And a FinFET or these 3D transistors, they are essentially 3D devices, so you need to look at in a 3D manner as well. If you usually take a cross section along the fin direction, it looks like this. So it doesn't look very different from a planar device. If you show somebody a cross section along that direction, there's a source and drain here, and there's a gate over here. It doesn't look very different from a planar device. So you really need to look at along this other direction, that is along this perpendicular direction, and if you look around that direction, then you can clearly see this this gate wrapping around your fin. And so this is a picture around your taken exactly at this cross section. And interesting thing is, looking at this picture, it looks like the fins are very nice and straight and standing like a square fin. But if you look at this picture, the actual TM which was published in June 2012, so that doesn't look like a very perpendicular fin, right? It looks like a tapered or more like a cone that you see on your construction zones. So that it doesn't look planar, and we'll talk why it's not planar and what are the pros and cons of keeping it exactly vertical versus making it like a cone. So the question, the first question we ask is why did they need to go to these FinFET devices? So the reason is that planar technology or planar transistors, they don't scale too well beyond gate lengths of 30 or 25 nanometer. And part of the reason is your gate oxide doesn't scale. So I've uploaded some videos which talk about scaling, but one of the reasons is that your gate oxide stops scaling, and your gate control on your source and drain is weak. But even if you assume that you have a perfect gate dielectric, so if you assume that you have a gate dielectric of thickness 0, then also you cannot control these short channel effects, because even if you have a perfect gate dielectric and gate dielectric of thickness 0, you can only control this region which is just below this gate, but you can never control this region which is far away from your gate interface. And the way people have been trying to so this is all the current that you can control, but you get this leakage current that which you cannot control. And one way that we talked about earlier we control it is by designing our source drain implant. So we make a lightly doped source drain air. We also implant a halo region, so we do a halo implant. But there are limitations of extending that approach as well, because it becomes very difficult to engineer all those implants and all those junctions in this in a space of say 5 or 6 nanometer. And also there's that halo implant causes if you have very sharply doped p-n junction with very high doping on p and n types, it causes a lot of leakage due to band-to-band tunneling. So you get all this bad current that you cannot control, and so your off current goes up, your subthreshold slope degrades, and you can essentially never turn off your device. So instead of a transistor, it starts to look more and more like a resistor. And so this was the reason that they really needed to improve the electrostatic. So to improve the electrostatic, another way to look at it is to remove all this bad current, right? So, or you bring your gate closer to your body, or restrict your body just till here, right? So there are multiple ways you can do it. One way to do it is essentially cut out all that region below, right? You don't really need it. So shown here is a simulation results, and what it shows is for a gate length of 25 nanometer, if you make your body to be 5 nanometer, you can cut out all that leakage below. So this red means high leakage, blue means very low leakage. If you reduce it even to 7.5 nanometer, you cut it down even more, and we are in this green territory now. And then if you cut it out even by 2.5 nanometer more, you are mostly in that blue territory where you have very low leakage current flowing from your source to your drain. So this is one way to do it, and it's called SOI technology, because you have this thin silicon hanging on this insulator or this box dielectric. So this is it's called ultra thin body SOI, because we have this very thin silicons in the range of a few nanometers. And so this is one way to cut it out. Another way to cut out this leakage is essentially go to a double gate structure, right? So if you put 2 gates, so the minimum the leakage path, if you have a double gate structure, the path where the leakage occurs is always in the center of the channel. And you can again cut this out by just making this channel thinner, And turns out, this double gate structure is nothing but a cross section of your FinFET device. So if you take your FinFET device and take a cross section along this direction, it will essentially look like that, right? It will look like you have this one gate here and this another gate here. And another way to cut it is essentially make these double gate devices. And the way to make these double gate devices, one way to make them is to have this fin and this gates on all sides, and you can again cut down on that bad current. And what happens in this case is your fin width, which is your thickness of this silicon, that becomes very critical, as I'll just show you in the next slide. But that becomes a very key parameter for scaling. So when people talk about fully depleted, I usually just tend to call them fully depleted devices, but they will throw a lot of terms at you. So let's just try to go over it so that we don't. If somebody says you in a corridor a MUC-fed device or a Tri-Gate device, you don't confuse between them, right? So this is a bulk planar device, and then if you have a thin layer of silicon on top of this SOI wafer, then it's ultra thin body SOI or UTB SOI. If you have two gates in a planar device, or many times you can use this bottom silicon as a gate, then it's a double gate device. A double gate device flipped over is a FinFET device. And the main difference between a FinFET device and a Tri-Gate device is that in a FinFET device, you have that thick dielectric on the top, so you don't use this top surface for conduction. But in a Tri-Gate device, you use the same thickness of gate dielectric all around. So it's a Tri-Gate device. Intel tends to call it a 3D device. Some people also call it MUC-fed device, but nothing to be afraid of. It's a very friendly device. It stands for essentially multi-gate fed device. And you can further try to improve your electrostatic control by extending this gate even deeper into your oxide and into your silicon, so that would become a pi shape. So it's called a pi shaped device, and then you can wrap it around further and it will become an omega shape. And the ultimate device which has the best electrostatic control is you have a gate all around device where it wraps around completely around your gate. So just walk through this is the cycle of improving electrostatics, and currently people are using hair. So we went already from here to there. We can go down a few steps along this path to further improve our electrostatics. So this figure kind of summarizes it well. So going from a planar to ultra thin body to a double gate to a Tri-Gate, what you do is essentially you improve your gate control. So you can reduce your subthreshold slope and you reduce your off current, and that allows you, if you want to move this curve this way for the same off current, and then you reduce your operating voltage, and you reduce your power, and hopefully you can get Intel can get into they hope they can get into tablet space, at least if not smartphone space, using this. So having two gates does help you provide better electrostatics, because you only control a certain thickness below your gate with one gate, right? If you have two gates, you essentially both of them are controlling this body thickness together. Versus if you had, say, a SOI technology, you would require a much thinner thinner layer of silicon to achieve the same electrostatics. So having two gates does help, because these two gates are acting in conjunction to control this device. So allowing your fin to become significantly thinner also allows you to scale your gate length. But essentially, if you scale it very, very thin, like if you make it like 2 nanometer, or if you have a 2 nanometer say SOI device, then even one gate is sufficient to control that 2 nanometer, right? So then probably your fin and your SOI devices are similar if you're going to very small thickness. So when we talk about this FinFET device, it requires you to keep in mind certain dimensions or keep in mind some important dimensions. So those are listed over here. So it requires a certain adjustment of frame of mind to get adjusted to it. So what in a fin width, in a fin device, you have current conduction happening on all these three surfaces. So the way you define your transistor width is you have two of these heights, so you have two of these vertical edges, so you define as 2 times your height of the fin, and then you have the stop surface, so the width of that is the width of the fin. So this is your width of one transistor which is in one fin device. Similarly, junction depth, if you remember from planar, it was defined by that implant, how deep we implant, right? In a fin device, it's essentially defined by just as what is the thickness of your width, because you implant the whole fin anyway, so your junction is just defined by your fin width. That's again a shift in terms of thinking as compared to your planar device. The gate length, many people confuse it, they think the gate length is different too, but the gate length is just the gate length of this fin, so it's just the distance between from this edge to that edge of a fin, so the gate length does not change. Ideally you get a much better electrostatic, so you can get away with your body doping. So in an ideal world, you should not have any body doping in your fin. And the width of this fin is a key parameter because it determines your subthreshold swing, or your electrostatics is just controlled by your that thickness of that fin. So if you have a very thick fin, then you don't get any advantage by moving to a FinFET device. It's only when you have a thinner fin you start to see this advantage of improving electrostatic, because now your gate can essentially control that thin fin which is underneath it. So again, the bottom line is that your fin width is a key parameter for scaling. Another important parameter is another important thing to keep in mind is that when you have a fin device, you have to scale your width and your length together, and that is emphasized in these two plots over here. So we define effective length and effective width. We define our effective length as essentially our gate length minus that junction that we formed in the source drain might diffuse a little into our gate, so we subtract that. We define our effective width as the width of the silicon plus this width that you get from your high K, and you normalize that with the dielectric constant. And all the electrostatics, it depends on the ratio of this L effective to W effective. So two key parameters for your electrostatics is your subthreshold slope. So think about it. So this is plotted as L effective versus W effective. Let's assume we have a constant width. So let's say we have a width of say 10 nanometer. So when I'm moving along this plot, what I'm doing is when I'm moving from low L effective to high L effective, essentially I'm reducing my gate length. Right, so when I'm moving along this way, for a fixed width, if I reduce so let's say my fin width was 20 nanometer, 10 nanometer. So when my fin width is 10 nanometer and my L effective or my gate length is also 10 nanometer, I get this ideal subthreshold swing. But if I reduce it, if I get let's say go to a gate length of 5 nanometer, then again my electrostatics starts to degrade. Similarly, same story here in terms of your drain induced barrier lowering, but the key parameter that I want to emphasize is that we need to, whenever you go to a FinFET device, you need to scale your gate length, you also need to make your fin thinner. So when we need to scale our gate lengths, we need to make our fins thinner. And another thing is, so I defined that the effective width is essentially given by this surface around this fin. So if we want to have more current in the same layout, one way you can achieve it is make your fins taller. So one way to improve your current is to make your fins taller. If you want to scale them, then make them thinner. Yes.
What's XUD?
What's what?
XUD.
XUD is underlap, or it's basically the diffusion of this junction. So is that this source drain, ideally it's drawn very sharply over here, right? But this implant or this junction can diffuse into my gate, and that's that underlap region, or that it's that diffusion that I'm labeling as XUD.